maybe even a couple minutes early, depending on if you have questions or not. So for those of you that haven't been here before, my name is Chris Rakes, and I am an assistant professor in the Department of Education in the Colleges of Arts and Humanities and Social Sciences. And this is our 5th session on advanced research statistics. Our first couple of sessions were about meta-analysis and some introductory stuff to structural equation modeling. The 2nd, 3rd, and 4th sessions were mostly about structural equation modeling and various aspects of that. And today's session is specifically about structural equation modeling and how we use it to look at latent mean differences. And so without further ado, I will go ahead and jump in on this. Your handout should have my website on there, also my email. So if you have questions for follow-up later on, you're welcome to email them to me. If you have questions about your dissertation, same thing. And I'm always happy to answer that. I have my Twitter handle on there. You might as well not bother. I'm never there. So, yeah, no, it's bad. Okay, so jumping right in. When we're thinking about mean differences, we're typically thinking about multiple groups, and a lot of times we're thinking about a treatment versus a control group. We might be thinking about boys versus girls. We might be thinking about majority race versus minority races. We might have that broken out into multiple groups. But one way or the other, we're thinking about grouping variables, and we're dividing up scores by those groups. And we're trying to think about, do those scores indicate that there are differences? And there are typically 5 questions that we are interested in asking. The first question is, do items of a particular measure operate equivalently? So if boys take this test and then girls take this test, does it act the same way for them? Or do they interpret questions differently? So that's really a question of reliability across groups. The second question, is the factorial structure of an instrument or theoretical construct equivalent across populations? So again, I've got this test, and I think that I am measuring people's confidence and their attitudes about education and their anxiety about testing. And I've got a certain number of items that I think are going to tell me something about their anxiety levels. But if I test it with boys, it could be that one of those items goes with a different factor. Whereas with girls, they might think it operates with that factor, or vice versa. So what we're thinking about is that if I have a factor structure, and I think particular items measure a particular construct, does that structure hold up across different groups? So again, this is another question of reliability. Are certain paths in a specified causal structural equivalent? So if we think that there are relationships between factors, so I think that high test anxiety leads to low scores on the test. That would be a latent structure that is causal. And I could say, does that work the same way for girls as it does for boys? Does it work the same way for my treatment group as it did for the control group? And if it's different, that tells me something about how those structures work for those different subpopulations. The 4th question, which is bolded red because that's the question we're really going to focus on today, is, are the latent means of particular constructs in a model different across populations? So we now come to this point where I say, okay, so in my field, I'm math education, so I talk a lot about achievement tests. And so other areas will talk about other kinds of scores just as much as I talk about achievement, but for the purposes of this, I'm going to stick with what I know. And I'm going to say, okay, so I take an algebra test, and I've got factors about analyzing analyzing a system of linear equations. I've got questions about modeling systems of linear equations, and I've got questions about whether or not they can just solve it and get a right answer. And I think those are 3 separate constructs. So I take a treatment group, and I do something that I think is going to really make a difference with how they learn this material. And I've got a control group, and I did a pre-test, and I do a post-test for both of these groups. Now I would like to know, if I take the means of those latent factors, analyzing, solving, and modeling systems of equations, are those means different for my treatment and control group? That's the question I'm really asking here. And then the last question is really more about measurement psychometrics. Does the factorial structure of a measuring instrument replicate across independent samples? So if I develop an instrument of some kind, and I think it's got 3 measures, whatever those measures happen to be, I go out and I do a pilot study, and I test it, and lo and behold, those factors worked out for the group that I tested. And I'm really excited about this. Question 5 is asking, if I went to another group, how likely is it that I would get the same results? Cross-validation. So this is really a question of generalizability. It is also a question of reliability. And it's all about how does the measure work. So at least 4 of these questions that I've listed here that can be answered under structural equation modeling are really about developing some confidence that the measures that we think we have actually do what we think they're going to do equivalently across groups. So that when we actually do think we have differences across groups, it's not just some anomaly because we had a bad instrument. Okay? When I was doing my dissertation proposal development, one of my advisors said to me, make sure that whatever you think you're going to do, you're not trying to develop an instrument at the same time. Use an instrument that already exists, that's already had some work done on it, that's been validated, that has some high reliability coefficients, because developing an instrument is a study all by itself. And if you really want to develop an instrument, that's your dissertation, not doing something to measure with that instrument, okay? And at the time, I just took his word for it, and I said, okay, I don't know what that means, but okay, that sounds great, because I don't want to add work to myself. So I took his advice wisely. Now I look back and I'm going, well, just thinking about what these questions are, thinking about what you would have to do in terms of sample collection and the amount of analysis, there might actually be in these 4 different, in questions 1, 2, 3, and 5, there might actually be 4 dissertations there if you really wanted to test an instrument, okay? Or it might be a whole dissertation that answers all 4 of those questions. Depends on the complexity of your instrument and what your design is going to be. The point being that if you're thinking about your dissertation and you're thinking that you have some sort of an intervention that you want to develop, and you want to develop an instrument to measure the effects of that intervention, you've now got 2 dissertations. Okay? So you really need to think about focusing your work. After I did all of that stripping away, and I thought I had a really nice tight dissertation, I got to my proposal defense, and my advisors and my whole committee came back and they said, this is really wonderful. You have 3 dissertations here in your proposal. So we're going to cut this stuff out. And that's a really good place to be, as opposed to them saying you haven't really said enough. So we had to go back and we went through and we cut it all out. And we really focused in on those questions. And I have to say that I blessed my committee many, many times during data collection and analysis, because they had cut out like 3 different instruments that I was going to collect data on. And it was a nightmare as it was trying to get everything entered, because it was my first time trying to do some of that kind of data collection. So it was wonderful not having that extra load. So we stripped it all down and we really got deeper into these and really figured out that there were some sub-questions in there, and really that even when we proposed it, there were some nuances there that until we got data, we just couldn't know that there were certain things there that we were going to find. So I got to my dissertation with the stripped down version from my proposal defense, and they said, this is great, you did exactly what we asked you to do. You had 3 dissertations, you cut it down to 1, and when you finished fleshing it out, you really still had 3 dissertations. It was just 3 different dissertations. Because I did. I mean, as I look back on it as an advisor now, and I say, okay, well, that could have been a whole study by itself, and this could have been a whole study. And I've actually continued that study line since then, and I'm about 5 years past the point, and my mentor and I still work closely on it, and we look back and we're going, well, 5 years later, we almost understand what it means. Okay? And that's a good thing, because we've really done a lot of work since then, and we're really starting to get a grasp on where this is going to go. Not all dissertations end up being a career line like that, but to the extent that they are, that's a really good thing, because it really sets you on your way. The point of all that is to tell you that if you're thinking about your dissertation, you're thinking about trying to develop an instrument while you are trying to do some sort of an intervention, you've got 2 studies going on, and you really need to narrow that down and figure out which one of those you really want to do, because doing both of them is too much for a dissertation. Okay? Let's move on. Most of the questions that I just asked, especially question 4, typically when people that have just started doing research think about questions like, are the means of 2 groups different? We think of some sort of an analysis of variance. That's where our mind goes. That's what we learn. If you're in intermediate stats, or if you've gotten to multivariate stats, you're thinking of either ANOVA, analysis of variance, ANCOVA, analysis of covariance, MANOVA, multivariate analysis of variance, or MANCOVA, multivariate analysis of covariance. So remember that the C here is whether or not you have some independent variables that you're trying to suck up some variance on. For example, a pretest. If I have a pretest and a post-test design around an intervention, that pretest is going to be a covariate because I want to account for all of that variance that the pretest can account for, and I really want to think about the differences that aren't due to the pretest. So I account for that, and then I strip it away so it's a covariate, okay? Multivariate, the M, that's not about your independent variables or your grouping variables or the number of groups, that's about your number of dependent variables. Most textbooks will say that with a multivariate analysis of variance or covariance, you should really limit the number of variables somewhere between 2 and 8. Once you get past 8 variables, you've really got way too much going on, and it really isn't capable of parsing that out very well. And the sample sizes that you need are so ridiculous to even keep it from making mistakes that it's really not worth your while. So that's sort of where we're coming from. So one of the first things I want to talk about is why do we even care about structural equation modeling? That sounds like a really big deal when I've got MANCOVA. Why can't I just do that? General linear model. So let's talk about why. So first off, analysis of variance, and I'll just shorten it to analysis of variance. I won't talk about all 4 of them every time. But understand, when I say any of them, I mean the whole family of analysis of variance techniques. But when we're doing that, the big word here is observed. It's the observed means. So remember that in my illustration at the beginning I said I had 3 different factors of systems of equations, and I might have 5 or 6 different questions that get at, say, solving or modeling or analyzing. And so I think that my students' ability to analyze a system of equations is a latent ability. But I think that I can look at 5 items on my test, and I can get a sense of how well they can analyze those systems of equations. MANOVA will look at each of those 5 items, and it will look at differences between groups on those 5 items. It will not do anything to look at the latent mean. Okay? It only looks at the observed scores. So there, right away, there's a whole level of variance that we're not getting. So the basic picture here, we've got equations. We've got an intercept, which is the mean, plus whatever individual error a person brings within that group to get the overall Y for that group. So I have T here in this case means treatment, C means control. Okay? So in terms of pictures, we've got our measured variable Y or multiple measured variables Y. We have group membership, and we have a residual term. So every time that you run an ANOVA or one of them, you have all those different lines that you've got the corrected model, the intercept, and then you've got whatever groupings you listed. Then you've got a row that says error, and then total. Well, that error is the residual. It's what was not accounted for. It was what was left over after you accounted for all of the covariates in your model. Okay? And that will include both prediction and measurement error. So let me explain what I mean by prediction and measurement error in case you're not familiar with those terms. If I take item 1 on my test, and I'm having a great day, I nailed it. I come in on Tuesday, I'm having a bad day, and I flopped on it. It's me, every time. Same item, every time. On any given day, I might perform differently on a particular item for whatever reason. Has nothing to do with my innate ability to solve that item. It's just the vagaries of the day that I happen to be testing on it. That's measurement error. And we want to minimize that because what we want is somebody's true score, not just the daily vagaries of whatever happened to be happening because I didn't have enough for breakfast, or I got rushed, or my car ran out of gas. All those things can really influence my performance, and so I have to make sure that that's minimized. So that's what I mean by measurement error. Prediction error would be I'm trying to predict a score in Y, and my ability to predict that could vary over time. So I may be able to say that group membership has a mean prediction, a slope, if you will, of that y variable with a standard error around it. That's the prediction error, is how wide is that confidence interval around my estimate of that slope. So I think that I can predict 30% of the variance in that model, give or take 5%. That give or take 5% would be my prediction error. And when you get that error line in an analysis of variance, all of that is lumped into one number, error. There is no way to parse it out. It also accounts for relationships in multiple y's. So if I've got 5 items, it will account for those correlations along with the group memberships all at once. That's what MANOVA will really do for you. Basically what it does is it says, are there differences anywhere? If there are, then we can strip it down and start looking at which variables it is. And if there are differences there and I've got more than 2 groups, then I can say which groups are different. So I basically keep scaling it down and filtering it so I avoid type 1 error, but really we're looking at matrices. Okay? Mathematically. So that's MANOVA. Now, here's what I really like to do. I don't really care about item 1. I don't care about items 2 through 20 either. What I really care about are those 3 factors that I'm trying to measure. I want to know how well can my students analyze, model, and solve systems of linear equations. That's a latent variable. And I've got 5 measured variables to indicate that. And in previous sessions, if you haven't been here, we've talked about how do we establish that relationship. And if you want to go back and look at those PowerPoints are on my website. There are also lots of textbooks out there to help with it. I think I've got some citations in there for you too. If not, you can email me if you're looking for a book. So in this model though, I have my measured variables y, and each one of them has a certain error associated with how well it predicts this latent variable. So I've got 5 items and each of them get their measurement error, and that tells me how strong those items are in a certain sense for that factor. I also have a factor loading here that tells me how strong they are. Okay. From there, I have my group membership, but now I'm not predicting the observed score directly with my group membership. I've now said something different. I've said that measured variable y is really rooted in what they understand of this latent factor, and the group membership could influence what they understand of that factor. So in other words, I'm predicting the latent variable, not the measurement variable, okay, not the observed score. And the residual on that latent variable is just prediction error. So sometimes you'll read that latent means will allow you to parse out measurement error from prediction error, and that's sort of true. But in terms of understanding how it's doing that, it's never aggregating them to begin with. It always keeps them separate. So it doesn't disaggregate something, it just never aggregates them to begin with. And again, it does that through matrix algebra where you've got multiple scores inside of a matrix and it can work on the entire matrix at one time. That's about as much as I want to say of the mathematics behind it right now. Okay, so there are some steps to being able to do this. The first thing is that we want to determine a separate baseline model for each group. So I've got an example here of self-concept. This is a psychology example, and in this particular study, which was not mine, it came out of a textbook, they had Nigerian students and they had Australian students, and they had no a priori assurance that the self-confidence factor or self-concept factor would actually work the same for Nigerians and Australians. So they needed to test that. So they went through and they said, well, what does it look like separately first? And we get the best model we can for each group, and then we put them together, and we call that a configural model. We haven't done any changes, we haven't restricted anything, we haven't tested anything. We just said, I got my best Nigerian model, I got my best Australian model, now lump them together, now I've got my best 2 models combined together. So now I've got them all in one spot, and that's sort of the next step to putting them together in a way that I can actually compare them, okay? Then we want to start testing invariance. So I actually struggle with the terminology on this. And I have to tell you that every time I teach it, and every time I study it, and every time I do one of these, I have to set up what my vocabulary is going to be because I can't keep them straight. Because we got too many different negatives, actually, is what really happens. So we have the term invariance. So variant means change. Invariant means it doesn't change. So an invariant parameter is equal. And a non-invariant model or a parameter is not variant. So in other words, it does vary. So they use a lot of double negatives, and you'll read in textbooks invariant versus non-invariant. Sometimes I just switch that to equivalent and non-equivalent. I have an easier time with that for some reason. So, so be aware that there's some terminology here that even if English is your primary language, there's a lot of loops you can get yourself caught in. So to test model invariance or model equality, I want to actually constrain different sets of parameters to be equal. So remember, I started with a configural model. I said I've got my best Australian, I've got my best Nigerian model. Now I'm going to say, I know how that fits together. If I just put them all in one model, I've got my goodness of fit indices. So what happens if I took all of those factor loadings and I said, I'm going to force them to be equal between the Nigerian and Australian groups? Does the model fit better or does it fit worse? And if it fits better, then those sets of parameters, those factor loadings, should be equivalent. And if it doesn't fit better, then they're not necessarily all equivalent. So we usually do them in blocks just to kind of save some time. But if they're not, then we would actually go through and say, okay, so not all the factor loadings are equivalent. Are any of them equivalent? So then we look through them one at a time. But if the whole block works, then the whole block works, and you move on to the next block. So we typically start with our factor loadings. Those are slopes. So going back, that would be these arrows here. So we would actually first start with those arrows, those slopes of how strong are the observed variables measuring the latent factor. Then we would go on to the measurement errors, and then we would go on to the observed variable intercepts, so those means, okay? So then the question we're really asking at that point is, are those common parameters equivalent? And in this case, do the non-academic self-concept factors behave the same way? So are they equivalent? Are they significantly different? Which ones are the same? Do they even have the same parameters? We found that out at the baseline model. Then whatever parameters are the same across the two groups, do they have the same values? So then the final thing is to determine which measurement parameters are equivalent and constrain them to be equal. So then, so that's really no new question. We're just kind of wrapping that up. We're going through the whole thing. Then finally, we look at means, variances, and covariances. So we sort of do this in steps. We start with, do the instruments work the same way? Do the factor structures work the same way? And we work our way up that once we've established what does and doesn't work the same way, and we force those parameters to be equal, then we look at the latent means, which are estimated from that model, and we ask if those are equal. So we've really controlled for a lot of different potential sources of non-equivalence before we ever actually ask the question if those means are similar or different. So it's a much more complex situation than just a t-test, right? Or an ANOVA. We're asking a lot more. So let's take a look at what this kind of looks like. So we have our general baseline model that I mentioned before. So I had these 4 factors, and I've got all these different variables that are factor loading on each one of those, and each of these factors are correlated, shown by the double arrows here. By the way, I would just, as a quick aside, one of the nice things about structural equation modeling is that you get to draw a lot of pictures and you can graphically demonstrate what you're thinking, which helps you develop a conceptual model and explain your conceptual framework to other people. Because if I didn't have, for example, this double-headed arrow here, then somebody would rightly want to know, why don't I think that this factor and this factor are correlated? Okay? So one of the first things I want to point out with this picture right away is that MANOVA really can't do anything with this, okay? you're not going to have a situation where we've got 1, 2, 3, 4, 5, 6, 7, 8, nearly 32 variables on this picture. You're not going to do anything in MANOVA that's meaningful with 32 observed variables. It just isn't set up to deal with that. It's too many correlations. You have to have a pretty large sample size to even get it to run. And at that point, you still don't have any assurance of reliability. And there's nothing in MANOVA that says question 1, 8, 15, and 22 belong on the same factor, whereas 5, 19, 26, and 34 belong on a different factor. It's just going to put them all together and just jumble them all up. So right away, we've already got a structure here from our theory that we can't establish in a MANOVA. So I have two groups with this. This is the Nigerians versus the Australian students. Non-academic self-concept, by the way, was what it said the dependent variables were for. These factors are about. By non-academic, we mean we can sometimes talk about self-concept in terms of learning math, learning English, learning social studies. In this case, we're thinking about things that are not academic. So things like, who am I as a person? How much do I like myself as a person, kind of thing. These are more psychology, not academic. So if we tried to do some kind of analysis of variance or some kind of a standard technique, we really, even if we can get it to run, how do you interpret it, right? You've got all these things going on, and it's really not easy to figure out where does the observed variable actually represent the underlying factor, and where is it just an aberration of the item? I have no idea. I mean, I don't know that it's not a great measure of the factor. Could be. I don't know either way. And if I don't know either way, then I've got nothing. Okay, so then step one, the baseline model. So we go through and we test this, and we found out that one of those items on the first factor for the Australian students actually cross-loaded, that it also seemed to be representing another factor. And I'm not going to go too deep into these. They're labeled differently, just factor 1 and factor 3 for the purposes of today. That same item also cross-loaded for Nigerians, so we added it. We also have, if you'll notice over here, that the unexplained variance of these two items was correlated. There was a relationship between them for the Australian students. If I come over here, it was not. So right away, this is a parameter that is non-equivalent across groups. So this is when I was saying we're going to compare parameters that are on both groups. This is one of those that right away, before we even start this, we're not going to compare this across groups because it isn't there for both groups. Okay. We have another error variance down here, covariance, I'm sorry, which is also in both groups. So we added a few things to the baseline model that I showed you in step 0, and some of those things were added for both groups, and at least one of those things was added for only one group. So as I wrote here, only parameters that are common to both groups are eligible for equivalence testing, because if it's not in both groups, then it's clearly not equivalent. It's already a done deal there. Okay. So I thought it would be helpful at least to talk about what the syntax looks like, because when I first learned a couple of different techniques, I was reading theoretical textbooks about what was involved in them and how it worked, and it took me weeks to figure out how to actually punch the buttons. And I think the fact that nobody thought it was important to say, where do you find the button to push that thing, is kind of awkward and frustrating and unnecessary. So even though this is not a seminar where I want to really go deep into syntax, I think showing you what this looks like and talking about how you would actually run one of these is at least a good place to talk about generally. So there are a lot of different programs that will run these models. You have a program called AMOS, A-M-O-S, which is pretty graphical in nature in the way that it works. It has a few limitations, but it's a pretty good program for baseline stuff, for just initial stuff that you're learning. It was the first program that I learned on. The very first program that was ever created to do these back in the late 70s was called Literal, and Literal actually is built on Fortran coding. It is almost totally non-graphic. All the graphical features were added after the fact. It's almost pure syntax, and it's almost like learning a new language all by itself. And it deals directly with typing in the name of the matrix. They have particular names for matrices, And you have to basically say all of the parameters about that matrix. Are they free estimated? Are they fixed? What's the fixed value? Everything is basically very, very manual, which has the advantage that if you know what you're looking for and you know how to do it, then you have full control to specify every single thing without any issues, because you have to specify every single thing. But there's a huge learning curve for Literal. The big thing that I liked when I learned Literal, it was the second program I learned, was that with Amos, I could just draw arrows and circles and rectangles, and it worked out nicely, and I could do some basic general stuff. But when I got to Literal, I had to start thinking about what were those matrices and what goes in them and how does this work, and I started understanding the underlying mathematics better. So as far as a learning curve, it was a great second program to learn. The program that I'm working on here, there, by the way, is also another program called EQS. I've never actually used it. It sort of has some graphical features. It also has some syntax. It's not quite as unfriendly as Literal, but not quite as user-friendly as Amos. But I've never actually used it. It was just one that I, no particular reason, I just never used it. One of the newest programs out is called M+. And M+ will do all kinds of things that no program I've ever seen before will do. I had to, when I first learned a couple of different techniques, like there's hierarchical linear modeling, and we had a program called HLM to do that. And there's item response theory, and there are programs specifically to do item response theory types of analyses. And then there was structural equation modeling, and there's particular software to do structural equation modeling. M+ will do all of them. And it will do latent factors on hierarchical models, and we'll mix them and match them. And it's really pretty straightforward that it's really the same mathematics, but it lets you specify things so that it can do all of these things all at once. So it's a very, very versatile tool. As you can see, it is primarily syntax. The syntax isn't even close to as difficult as Literal, not even a tenth. I actually learned it through a couple of seminar sessions and then just started practicing with it. It was really not that hard, but of course it was the third language, so I kind of had an idea of what I was doing by the time I got there. So most classes nowadays will start people off with M+, because it does have a graphical component that you can use, and the syntax isn't that difficult. I mean, you just basically say things like use variables are, and that's it. I mean, it's pretty straightforward. So, so you say, here's the data, here's where the file is, here's its path. Here are the names of the variables in the order that they appear in the data file. Here's what I use to mark missing variables. And M+ does have this weird thing, this use variables thing. If you don't use all of the variables that are in your list, you have to declare which ones you're going to use, because it won't put the non-used variables into the matrices to compute anything. So it needs to know it right away. It's a little bit of a quirk. None of the other programs ever need that. They just don't use anything that you don't use. And then you have to tell what kind of estimator you're using. It has some defaults for that. Not all of this has to be there. In this case, I was using a restricted maximum likelihood estimator because I had non-normality in the data. So again, that's really not that big of a deal. So if you're looking at multiple groups in this particular program, the data for each group remain in separate files. When you put your data files in, you don't have variable names in there, it's just lists of numbers. That's why the order here is really important, because if you get it out of order, then you get out of order. It's actually pretty easy to do that. You can just make the file in Excel, take your row 1 out and copy and paste it as text, and then delete row 1 from your Excel file, and you've got your set. I mean, it's pretty easy. I already talked about that. Okay. So the rest of that was the first half of the syntax. So for the second half, then we want to talk about, first off, our model. So we got to set up the model so that it reads the pictures that I showed you earlier, where I've got 4 factors and I've got roughly 8 items for each one. So here I've got my 4 factors that are being measured by the list of variables. So now the computer automatically knows that I've got those 32 variables and that I want them to be forced onto these factors. By the way, what if I did this and I had those factor connections wrong? Well, that's why most of your textbooks, all of your good textbooks, will emphasize from page 1 and keep emphasizing all the way throughout the book that no matter what analysis you're doing for structural equation modeling, you have to have a strong theory for it. So in other words, I can't just make these up. I mean, I can just make them up, but it doesn't mean anything at that point. I need to have some reason for saying that I think that these variables measure that factor, okay? Typically because they were developed to do that, and somebody's done some validation on the instrument to say, yes, they actually do. Okay, so this is sort of a weird thing that happens with grouping. In M+, you have, in structural equation modeling, you have to have a reference variable, so all the factor loading gets fixed, but we need to know the factor loadings because we're testing for invariance. And so we actually have to estimate those to be free, and then we estimate the variances of these factors to be fixed. We start off with factoring, with the factor means constrained to equal 0 as just a baseline to test and say, like a null hypothesis, are they different from 0? Then once we get done specifying everything that is common to both groups, then we specify the things that are specific to our subgroups. So the only thing that was unique to the Australian group, remember, was that one error covariance. So I've got that marked here. And it's sort of intuitive if you think I've got two variables that are correlated with each other, and the code word for that is with. I think that I've got 4 factors that are measured by a series of items, and the code word for that is by. So it's fairly intuitive once you get the hang of it. It's not that big of a deal. And by the way, M+ does have, you can point and click and say, here's what I want this model to do, and it'll create the syntax for you. Most programs will do that at some level. Okay, and so then we also have intercepts in our model, and in this case, the default is that they're constrained to be equal, and we don't want them to be constrained, so that we can actually measure them. So then we go through our steps. We test the factor variances, the error covariances, the factor loadings, which are the regression paths, or slopes, if you will, and then we finally get to the latent means. And so I've got a small result table here. This is quite truncated, actually. In this case, these first 8 models that I've labeled as FL, those are different factor loadings that I was testing. And so we've got some different fit indices. One of the things that's sort of interesting about, say, a MANOVA is you get a result, and you might get an R² to go with it, and that's what you got. You got your results. That's what they are. In this case, we get things like that. You get an R² across, we get multiple correlations inside the results, but we also get what are called fit indices. And these fit indices are described to tell us how well did we do? How close were they? And if you go back to, I think, maybe session 2 of this workshop series, we talked about the fact that basically what the program does is it takes your observed data and it says, based on that, here are what all of our errors and covariances are between all of these observed variables. Then we take the model that you set up and we say, if that's true, if the model that you set up is true, what would the variances and covariances be between these? How close are the observed to what we call the model implied variances and covariances? So we're testing matrices and we're saying how close are they, how different are they? Then once we do that, we have to figure out a way to measure what we mean by how close or how different are they. The more different they are, we would say it's not a good fit because our model didn't fit the data. And the closer they are, the better fit. The model did fit the data. And of course, we have to also be careful because the data are only one sample and we don't want to overfit to the data. We want a great fit, but not so great that it only fits that sample and nothing else, so it wouldn't cross-validate if I did it again with other samples. So we have lots and lots of variables that can do that for us. I've picked a few that span the different ranges. Each fit index has its own set of strengths and weaknesses, and they sort of complement each other. There are different types of fit indices that are based on different things. For example, some fit indices are highly dependent on sample size. Others don't even use sample size in their measures. Some of them are very sensitive to non-normality in the observed variables. Some of them couldn't care less. You have some that, let's see, I got non-normality, you got sample size, what did I forget? Lost it. Yep, lost it. They all have different strengths and weaknesses. Residuals, yeah, that's right. Okay, so what we typically do with this, I could go through a whole litany of strengths and weaknesses for all of them, but I'm not going to be able to remember all of them off the top of my head, and they're all sort of different. So chi-square is our basis. Chi-squared is almost perfectly correlated with sample size. So you get larger sample, and you get more chi-squared. I remember the other thing, complexity of model was what I was thinking of earlier. So if I get lots of parameters in the model, some of these will just automatically say a more complex model is better. So what we do then is we measure several of them that have different strengths and weaknesses, and we look for a consistency across the picture. And so, for example, I have my CFI is the comparative fit index that I really want it to be greater than a 0.95. And if it's above 0.90, that's not bad. And you see here I've got a 0.909. RMSEA is actually based on residuals, and we want it to be less than 0.05. Smaller is better, as opposed to CFI where larger is better. And we see here that we want an excellent fit is 0.05, and we've got a 0.042. Not doing so bad. SRMR, we want less than 0.08. We've got a 0.09, which puts us at the adequate range. And then for ECVI, we just want a smaller, it's more of a comparison. I'll come back to ECVI in just a second. Because while I was using a robust maximum likelihood estimator, I have to adjust that chi-square to take into account the robustness. There's a scaling factor that goes with it, and that's what all of this is going on over in this section. But what I want to point out here is that I had a moderate fit from CFI, I had an excellent fit from RMSEA, I have a moderate fit from SRMR. So I'm probably not going to say it's an excellent fit. I'll probably say it's not bad. I might be able to do better. Now, if that isn't specific enough or technical enough for you, that's okay, because it's not technical or specific enough for me either. What I'd really like is that if it's not good, all of them are bad, and if it's good, all of them are good. That's what I'd really like, but sometimes data don't work that way. And so we go back, and that's why there's another model. We see if we can do a little bit better. And you see that when I did whatever that change was here, we went up a little bit in the CFI, we went down a little tiny bit in SRMR, and our RMSEA didn't change. RMSEA was already showing excellence, so whatever was going on in these data, RMSEA wasn't really detecting it, okay? Think about what would happen, though, if I had stopped at RMSEA by itself, and I just run and said, I've got an excellent fit. Well, I just missed 3/4 of the picture because it only looks at one piece of it. So I keep going until I actually get down to the end of this. I've got 0.919 for CFI. I got down to 0.04 and down to 0.084 for SRMR. Much better than I started with. They did show statistically significant differences in some of these reductions in chi-square, so they were worth keeping the changes. But I got to a point here where there were no more changes that I could make to the factor loadings that were called for both by theory and by the data. And so I was done with the factor loadings. That's the best I could do out of this. Then I went on to the errors, and when I made these changes, when I held all the errors to be equal, it went a little bit stronger for CFI, no change for RMSEA, no change for SRMR, and my chi-square barely moved. So it really didn't change anything. So I'm probably going to say, no, they're not really equivalent. Just leave them alone. So that got lost. Then I go on to my intercepts, and I checked those out, and then I got to the end, and we looked at the factor means, and I said, are those equivalent? And we get here, and we never really got higher than 0.92 on the CFI. We ended with 0.915, but our strongest was 0.040. We actually got our SRMR all the way down to 0.057. And then let me talk about ECVI for just a second. So I haven't talked about it up to this point because it's a comparative index that's meant to help keep us from overfitting a model to particular sets of data. So as I increase parameters, ECVI will penalize us for that. And so what we want is every time we add a parameter, we want ECVI to go smaller, because if it goes larger, then we're overfitting to the sample. And so as you can see, we pretty much went steadily down here all the way through until we got here to this invariance model 37. Oh no, that actually went down too, I'm sorry. And then we went up just a little bit here with the factor mean. Not a huge difference. We got a pretty big jump here. And what some people will do to cross-validate even from ECVI, especially if you got something where it's like, well, it looks kind of like model 37 is a little bit stronger actually than model 40, except for SRMR. It seems to be a bit more parsimonious in terms of it doesn't have extra parameters that we don't need. So what would happen though if I went to a different sample? Would I get the same results? So what some people will do is that if they have a big enough sample, before they do any analysis, they split it into random halves, and they do what's called a calibration, where they do all of this kind of work, and then when they get done, they go see if it worked the same way with the other group. So they cross-validate it. But you have to have a big enough sample to start with that. So then there's decision time. We've got all these data, we've got some estimates here, and we've got some means, and we see that this two-tailed p-value shows that 3 of the 4 factor means that were estimated were statistically different from 0. Whereas the Australian means, where we had originally constrained them to be 0. Don't know where that came from, but okay. There we go. Sorry about that. So then, if the Australian mean was constrained artificially to be 0, that doesn't mean that the mean was 0, it means that we forced it to be 0. Because we're not necessarily concerned with whether or not the mean is 0 or what its special value is, as much as we're considering, are these groups different? So it's a reference point. Well, this mean for PSCAP is statistically different from 0, and this one is 0. So now I can say with some confidence that the Australian mean for that is statistically different from the Nigerian mean, and the Nigerian mean is higher. I can also say that for the third mean, and I can say that they're different for the fourth mean, but the Australian mean is higher. And for the second one, I would say that they're not really different. And notice that we're doing this for 4 means, not for the 32 means. Right? Not the observed 32 variables, but the 4 factors behind them. Okay. So that's sort of latent mean differences. And so I think we still have a couple of minutes. Yeah. So I think we got some time for questions. Does anybody want to ask questions? I went through that fairly quickly.
So do you ever, out of curiosity's sake, say, what if I do change how the factors work, just to see what pops out?
That's a great question. What typically happens if we don't have a strong enough theory to know how those factors are supposed to be laid out, we'll usually do something with an exploratory factor analysis. Like the factor analysis you'll run in SPSS, where it will give you eigenvalues, and it will say you've got, if you keep 16 factors, here's the percentage of variance. If you keep 5 and whatnot, you decide how many they are, and then you look at the factor loadings to see which factors go with which variables. That's often done prior to something like this. We usually start with confirmatory at this point. If you haven't done the exploratory first, you have to be really careful. You have to use a different data set for the exploratory. Because if you run the exploratory on a data set, and then you run a confirmatory on your results from the exploratory on the same data set, it's circular reasoning. Because, of course, I figured this out from these data, and then lo and behold, I confirmed that that was what was happening in these data. So it's just running yourself in circles. So you have to have a different data set if you're not sure about that. Typically, if it's not developed enough to do this, then they'll do an exploratory factor analysis, and they'll talk about what those means are just from the observed standpoint. Because you can do in an exploratory, you can get factor means estimated they're really still just observed means. I think they're typically weighted averages based on the number of items and the number of sample per item. But it's better than just doing items. It's not as good as this, or it's not as far along as this, really. It's a great question. Yeah?
Can you use Mathematica to calculate any of these?
Mathematica works on a lot of different things. I'm not sure whether it will do something like this or not. I know that that SAS will. This is more statistical analysis. Mathematica, I think, does more functions, equations. I think it'll do some statistics. I don't really know its capabilities. I know it wasn't designed to do this. I know even SAS wasn't designed to do this, and SAS is probably closer to Mathematica than M+ is. But SAS to do stuff like this, they really had to add a patch in to make it work. So my guess is no, but I haven't actually tried.
Can you repeat the questions also?
Yes, I can. So the question was, will Mathematica do this kind of analysis? And my answer was, I've never tried it. It's possible that you could possibly make a patch to make it do that, but I don't think I know it wasn't designed to do that, and so it is possible that you could program it to do something like that. I mean, it's really just matrix analysis, so there's not necessarily a reason why you couldn't program it to do it. On the other side of it, that's a lot of work, and the programming's already been done on other programs, so I probably wouldn't. Yeah.
What about SPSS?
SPSS will not do structural equation modeling, not even close. So I'm sorry, the question was, will SPSS do it?
So computer science would do folded cross-validation where you withhold like maybe a third, or even a tenth and 9/10, and then run your.
Yeah.
Do you ever do that?
Yeah, so the question was, we can withhold different percentages of the sample out and run the data with that. And the question is, do you ever do that? And the answer is sure. At this stage of the game, the most common is to do two, just do a split half.
Yeah.
Most often because the sample sizes needed to run these are in a couple of hundred minimum. So getting a sample size to be able to divide it into 5 or 6 sets is probably pretty hard. But there is an SPSS, if you're doing an exploratory factor analysis, there is a process called parallel analysis that does something like what you're talking about, where it will make like 1,000 random data sets and run these things to look for factors that are not significant improvements on the model. So I wouldn't do it necessarily here, but mostly because of sample size issues. Sort of a side corollary note to that question is that most of these programs do have something, if you wanted to do multiple imputation, or if you need to do some sort of missing values analysis, they have some way to put in multiple imputation data sets to where you can analyze all of them at once. And SPSS does also, by the way, if you haven't used that before. And it will create your multiple imputation data sets. Okay. Other questions?
Can we get a feel for the fields and disciplines around the world?
Oh, sure. So the question was, what are some of the fields that might use this? And the answer is that it's pretty wide. So I'm in education. Psychology uses this a lot. I've seen people in biology, public policy, government, social work, pretty much anywhere that we think that there is an underlying factor that's not easily measurable, it can be used. So I've seen it used in mathematics, and I've seen it used for everything. So something as far away from that as possible. I had a person that was in social work that she had a set of data about hospice care workers and social stresses that they have for informal hospice care workers. So that would be people like a child that is taking care of an elderly parent, so the stresses that they have after they've been introduced into hospice. That's about as far from my field as it can get, and we use the exact same analysis tools. I've seen them used in biology for thinking about things like, are there differences between different structures in the water for how a food cycle works in a particular set of ocean areas? So it's pretty wide.
We use it and slightly differently, but we're trying to find the latent variables in artificial intelligence.
Yeah. Right.
We have a lot of observed data, we don't know what the latent factors are.
There was one of the seminars that I attended from one of the guys that wrote the textbooks on this. One of his opening theses to the latent mean differences was that most people that use MANOVAs ought to be doing this because they don't actually care about item 1 versus item 3. What they care about is the factor underneath of it. So pretty much any place that you could do an analysis of variance, you can do this. Other questions?
Can I ask a question just of the group? I'm just wondering where are your gaps, if you have any? I know some people are here just to learn, sort of observe something new, something that you might not have had in some of your classes, but in terms of your research, your dissertation, your thesis, where are some of your gaps, and do any of your gaps connect to some of the structural equation modeling that Dr. Rakes is covering? Or is it such that you're just not sure what the gaps are yet? You're just thinking, let's just gather information and I'll know it when I see it and it can fill the hole.
Question. So this presentation is used a lot of background that you have in statistics, I guess, or I guess what kind of classes do you need to have a background into really?
Oh, that's a great question. So the question was, there's a lot of statistics here, and what kind of background do you really need to be able to do this? I started off just like everybody else in here in my doc program with a basic statistics course. Then I went to the intermediate statistics course, which was really, in my class, that was half a semester of ANOVA and half a semester of linear multiple regression. Then we went to the third class was sort of a multivariate statistics class where we focused on MANOVA, MANCOVA, ANCOVA. That class barely got to exploratory factor analysis at the end of it, but that's pretty typical for that class. And that's at the level that's sort of required. And so from there, this stuff sort of jumps on after that. I think if you've got multivariate, you're ready to start thinking about these kinds of things, and you could probably do it in a follow-up class after that.
And these classes were, I guess, like what level for them? Undergrad to grad?
Oh, this is all doc. All doc level. So these were all graduate level. So most of your doc programs here at UMBC will require a series of 3 stats courses, a beginning, intermediate, and multivariate, some variation of that. So I had those 3, and once you've got those 3, you can pretty much jump into this.
I think one of the reasons that Dr. Rakes started this seminar is because he noticed that in doctoral programs, ours and some others, that they weren't getting to this level. And so
And that's not uncommon
to
for
make sure
universities.
that at least you were introduced
Right.
to this level, because I talked to a number of graduate students who said they didn't even know this existed.
Right.
In terms of the level of statistics and where you can go in terms of analyzing your data. So he wanted to make sure that you were introduced to it.
So, I'm a computer science graduate student, and so we're not required to take any stats.
Right.
Computer science. We had to take 355 from the undergrad.
Right.
So that's why I'm asking. Because this
Right.
is-
So different programs have different requirements. And so the question, as I understand it, is that I'm in a program that basically doesn't require a lot of stats. We had 1 stats course. And most often that happens in a program that is a professional program, or it's a skill-based program, that it's not a research-based program. If you're in a master's program that requires a thesis, you're probably going to have certain courses that are required to do some of this kind of research. If you're in a doc program, I would be shocked if your program didn't have at least those 3 courses that I listed earlier in it. But if you're trying to do research and your program doesn't require them, there's usually some elective components that you can try to select those.
So if I can speak to that,
Yeah,
being in engineering, when I was in engineering, we didn't have any of this
Right.
at all. It wasn't offered at our level, and I don't know if they thought that we needed it until later on when we started doing other kinds of research and looking at specific problems and looking for solutions, and then trying to find out how to do some good, rigorous research. We ended up going to the social scientists and to other people in other departments saying, help me, I'm trying to put this together and I have no idea. I know how to program anything, but I don't really know how to do this subject testing kind of thing and all these other pieces. And so it was then that as an advanced doctoral student, even past candidacy, then we started saying, okay, well, maybe I should take a stats course and try to figure this out, maybe a research methods course and try to figure it out, and then work with other people. And so sometimes you don't necessarily always have to be an expert in this area, but if you know what some of the issues are, you can at least ask some colleagues where they can help you, or you can at least give them the terminology to say, I think that this might require a linear regression. I think this might require some kind of meta-analysis because of this situation. So having this kind of introduction, even at levels of people in computer science, engineering, you never know where it might take you, whether it's now in your doctoral program, as a postdoc, or even as a faculty member later when you start doing collaborative projects and they bring you in on a team or as part of a center. So having some of this, extra background, this sort of co-curricular background can help in that regard.
Yeah, if I can piggyback on that a little bit.
Please do.
When I started my doc program, I was a classroom mathematics teacher in high school. And I absolutely love teaching high school math. I still love teaching high school math. And I had a little bit of an attitude on me when I walked into classes because I'd already gotten my master's degree and sworn I was never going back to school. And then all of a sudden there I was back in school. And so I sort of had this attitude for my first 2 years that I'm staying as long as I like this, but I love my life, I love my job, and if I don't like this, then I don't have to do it. So keep me happy was my attitude. And luckily, I had a mentor that smiled and said, yeah, I don't really care. We're gonna do this because this is what you need to do. But what he actually said was, we need to think about what your career goals are. And that was really difficult for me because I didn't have any career goals at that time. I wanted to do a doc program because I wanted to learn more. It was a very abstract sort of idea. I didn't have any really well thought out career goals. And so it was really hard for him as a mentor to help figure out where I was going. But he laid out a matrix for me one night that said, if you're thinking about teaching at the college level at some point, then let's look at some of these different levels. And he had it broken out by a 4-year liberal arts college. What kind of research experience do you need to be able to succeed there? If you go to a regular college that offers master's degrees, what would you need to do that? If you want to teach doc programs that are sort of professionally based, like an EDD program in my field, you need a certain level of research that's higher than those others. But if you want to go to a Research 1 university and you want to conduct research and be a research professor, you need this level. And it had all kinds of stuff that was nowhere on the rest of the list. And I was like, well, I don't think I need that. And he said, well, okay, but you don't know what you want to do, right? So why don't I teach you over here on this column, and if you want to do one of the ones in the back, nothing's stopping you. You can always quit, but if I teach you onto this column because you don't know what you want to do, and in 10 years you decide you want to do this, go do another doc program because that's what you're going to need to do. So he did. So kind of cycling back to that question. Most of the classes that I took to learn how to do this didn't exist at my college. So I told you the basic ones, and then I said I sort of just kind of, I just kind of jumped off at that point. Let me explain what jumping off meant. Structural equation modeling wasn't a course, so my mentor had started a study group. Basically, he wanted to learn it, so he got some faculty together, they started a study group for it. Once they figured they had a pretty good grasp of it, they started teaching the classes. I was in the second cohort of people that took the class. When I got done taking the class, he said, that's great. So next semester, you're going to do an independent study, and you're going to help me teach this course. And so most of my electives in my doc program started turning into independent studies. So I ended up co-teaching structural equation modeling 3 times with those 2 professors. They were team teaching already, so there were 3 of us teaching. When I say co-teaching, I don't mean I sat in the back and graded papers for them. I mean, we met once a week before the class met, and we divided out tasks, and I had to teach part of the class. And I had to help answer questions, and I was a full member of that team. So it was a very unique experience that he brought me in on. And it was a learning experience, it was educative for me, and I developed some skills and whatnot. There was, I mentioned hierarchical linear modeling, same sort of pathway he did with that for me. I took the course once with him, and then he made me teach it with him a couple of times. Then they hired an actual psychometrician, and she taught the course, and they made me be her GA. And so I got to co-teach the course with her as her GA and learned all kinds of things because she actually knew what she was doing. And which was really funny because I would ask her questions. She's like, you know, I don't know the answer to this either, right? And I'm like, no, you're Jill, of course you know the answer to this. You're the psychometrist. She's like, yeah, we need to get over this really quickly. So I did that. He had me co-teach a psychometrics, intro psychometrics course to get some of the stuff I mentioned, item response theory earlier. That was where I sort of got my basics on that. So my doc program involved a lot of independent study because he said, if you want to go to that column, then the courses don't exist here. So we need to sculpt this out for you. And so that was where it ended. And honestly, those experiences are how I landed where I am today. So he also, on the side that wasn't part of any classes, there was a team at our university that was trying to do a project that was just a regular old MANOVA. Well, I had done MANOVA in class. I had never done one for a real research project before. He stuck me on that team and said, go work with them, be their methodologist. And I had to figure it out. That was my very first paper that I got published. And by the way, I got a call or an email about a week and a half ago on my very first paper that somebody was trying to conduct a meta-analysis and they couldn't find some of the data they wanted and wondered if I could get it to them. All they wanted were means and standard deviations. And doing meta-analyses myself, I was over there going, what? I published a paper without means and standard deviations? No. But it was my very first paper, and I looked back and I was like, well, crap, I did do that. So it wasn't a big deal, actually, and I will say with some pride, 5 years later, 6 years later actually now, I was able to go back and it took me about 30 seconds to find the data set and run those analyses. So that's strong data organization and file management is important in research because these questions come up a long time after you think the paper's dead. People are still using it. So being part of that sort of bolsters your confidence because that paper got published fairly easily. Just one round of revisions, first journal we submitted to. So that's a nice place to start. I had another professor that taught us meta-analysis that the class project was to replicate a research study that was a meta-analysis in our field, just as a way of practicing based on data that have been done before. And sometimes one part of the projects were, are there weaknesses in the study that you see that you could improve on? And in the paper that I picked, I happened to find a lot. And so we realized that instead of having a sample of 35 studies to analyze, I was going to have closer to about 100. And my professor said, there's no way you're going to do that in one semester. So I picked a little subsample for the class project, and then I did an independent study in which we continued working on this, and that was my second paper that got published, and it took us about 6 months. So I guess maybe a stronger answer or a more complete answer to your question was, I took the basics classes that were available to me. And then at that point, my mentor looked and said where I needed to go and said, if you're going to go there, we need to create experiences for you to get you there. And then we did. And a lot of that ended up being independent study. Most of my electives in my doc program were independent studies that were way more involved in class projects and spanned more than a semester. So you really have to work closely with your mentor to get those kinds of things going. Those are great questions. Well, if you have other questions afterward, I will be around here for a few minutes and then I'm going to head out. You can always email me if you have questions about your dissertation. I actually did field a meeting after the last session where somebody was wondering about the data analysis plan for her dissertation. We hammered it out in about 45 minutes. So I am available for those kinds of consults. So thank you very much. And for those of you that have been here for multiple sessions, thank you so much for supporting these sessions and for being here. And I hope that it was worth your time and your effort. And have a wonderful rest of the semester.
Thank you, Dr. Rakes.
Thank you.
Thank you very much.